Hello everyone, and welcome to our deep dive into the pipeline of failure. Today, we are going to decode how large language models reason, or rather, fail to reason, when it comes to hardware. We'll explore new error taxonomies and uncover the hard ceiling that currently limits RTL generation. Let's start by looking at what we call the cognitive distortion of hardware. LLMs are overwhelmingly trained on software languages like Python or C. Because of this, they build deep cognitive priors for linear, step-by-step execution. But hardware, like RTL and Verilog, is fundamentally different. It demands parallel temporal reasoning, where all logical operations on each signal path happen independently and simultaneously. This creates a paradigm that is highly prone to race conditions, completely clashing with the model's linear mindset. To understand where models go wrong, we can view the EDA pipeline as a cognitive filter that categorizes hardware correctness not as a simple binary, but across different levels. First, the parser catches L1 syntax errors, where the code simply fails to parse. Next, the synthesizer and linter catch L2 semantic errors, meaning the code parses but violates static physical constraints. Finally, in test bench simulation, we see functional errors split into two types, L3S, which are solvable errors that pass in subsequent rollouts, and L3U, which are unsolvable errors representing a true knowledge gap. We mapped these out into a taxonomy diagnostic matrix. If a model fails at L1, it essentially cannot speak the language, which can be fixed with basic supervised fine-tuning, or SFT. If it fails at L2, it misunderstands the rules of physics, which SFT or reinforcement learning can address. An L3S failure means the model actually knows the answer but lacks focus, so we can fix this using inference-time scaling like best-of-n sampling. But an L3U error? That's a fundamental knowledge void requiring architectural or pre-training improvements. Let's look at the anatomy of these failures in practice. An L1 syntax error might just be a missing end module keyword that shatters the code. An L2 semantic error could be a missing reg declaration that violates procedural constraints. An L3S error is often a simple logic mistake, like a rollover threshold, that the model can successfully correct in another attempt. However, an L3U error reveals missing core domain knowledge, such as failing to understand Galois XOR taps, making it completely unrecoverable. When we analyze different models, three clear archetypes emerge. Syntax bottlenecked models shatter before functional testing even begins, prioritizing general formatting over hardware logic. Semantic challenged models have perfect grammar but fundamentally misuse HDL constructs. And functional bottlenecked models generate perfectly compilable code that ultimately fails at the test bench due to deep hardware knowledge gaps. The key insight here is that even the absolute frontier models plateau at a 90.8% pass rate, which is gated by a hard 2.2% L3U floor. But there is a silver lining, which we call the inference-time opportunity. Interestingly, RTL specialized models achieve near-zero compilation errors but register the highest L3S rates. This is actually a paradoxically good signal. It proves the model possesses the required hardware knowledge but applies it inconsistently. Because these errors are recoverable by simply sampling more rollouts, domain-adapted models are uniquely positioned to dominate using inference-time compute. You might wonder, can't we just fine-tune these errors away? The surface convergence gap shows us why that's tricky. Supervised fine-tuning primarily acts as a syntax rescue. It eliminates L1 and L2 errors by teaching models how to compile, but it concurrently exacerbates deeper functional failures. It pushes previously uncompilable code into the test bench, revealing pre-existing knowledge gaps. In short, alignment merely moves errors forward through the pipeline. We see a similar effect with reinforcement learning. This is the RL paradox. RL creates a selection pressure that drops validation compilation errors significantly. However, because the model still lacks holistic hardware understanding, these newly compilable rollouts simply crash deeper in the pipeline. Functional errors actually expand as testing begins. Looking at the timeline of a model's brain over 500 training steps, we realize that training convergence is a mirage. We see a rapid collapse of syntax and semantic errors early on, but a stubborn persistence and even widening of functional gaps. The total number of wrong rollouts stays surprisingly similar. They simply progress further through the error pipeline over time. This brings us to capability stabilizers versus destabilizers. We found that pure SFT can cause violent regression, where previously solved problems suddenly become unsolvable, trading old knowledge for new. On the other hand, general domain RL pretraining acts as a critical capability stabilizer. It maintains perfect stability, allowing the model to add new RTL capabilities without shedding its existing ones. So what exactly is the model struggling with? Our heat map of hardware complexity spells it out. Tasks like arithmetic or wire vectors are universally accessible because they share algorithmic structures with general software programming. But tasks requiring multi-step, parallel temporal reasoning, like state machines and counters, remain a universally hostile persistent blockade across all models. At the very top of this complexity are the unsolvable 6. These are specific problems, like creating 8D flip-flops triggered by positive edges, or complex multiplexer constraints, that have a 0% pass rate across 17 different models. They represent a hard L3U floor. They require non-standard specifications or intricate temporal reasoning that inference-time compute cannot fix, and they are currently immune to alignment. To break through, we have to look past a single model. We call this the diversity panacea. Our epiphany was that the vast majority of unsolvable errors are not intrinsically unsolvable, they are model-specific knowledge gaps. While the best single model solves 148 out of 156 problems, a collective brain combining the union of 17 models solves 150 problems, hitting a 96.2% success rate. The future of hardware AI isn't endless RL on a single architecture, but routing and ensembling across diverse model families. To wrap up, we need to fundamentally rethink the hardware AI pipeline. First, we must recognize that alignment mirage, SFT and RL don't instill new hardware logic, they physically shift errors down the pipeline. Second, we need to leverage the inference opportunity, utilizing best-of-n scaling to capture stochastic successes for L3S errors. And finally, to breach that 90.8% ceiling, we can't just rely on more alignment, we need massive temporal reasoning datasets and diverse model ensembles. Thank you.